Hello everyone, welcome to this seminar of FEA Analysis of Cable State Base using MIDAS. My name is Alok Singh Tomar. I'm from Rambol. So let's begin this seminar. Agenda for today's presentation is that I will first give a brief introduction about myself, and then I will also give an introduction about my company Rambol, and then I will present the brief history of Cable State Base and talk about its load path, and then I will also present the general characteristic of cable state bridge and its comparison with other kind of bridges, and then I'll explain the structural components of the bridge, and will also present the advantages, and then I'll present a case study on iconic bridge where MIDAS civil software and MIDAS FEA Annex software is being used, and I will also present the longitudinal analysis, transverse analysis, and local anchorage analysis of pairs. And then I'll also talk about the methodology to evaluate the deck reinforcement using above three analysis. And then I'll explain the design challenges and recommendation, and followed by a question answer session at the last. This is myself. My full name is Alok Singh Tomar. I'm a member of Institute of Engineers, and I have graduated with BTech and MTech degree in civil engineering from IIT Kanpur in year 2010, and since then I have been working in civil infrastructure industries. I have more than 14 years of experience. I work with projects related to bridges, airport, arenas, malls, special structures, temporary works, and offshore structures. I also worked on some international projects such as E45, new overpass Tiger Bridge in Denmark, Mumbai Metro cable state bridge Shun Bridge in India, RA256 South Sura Road Bridge in Kuwait, Doha Link Bridges in Kuwait, Hong Kong Airport Terminal T2 and Abu Dhabi Midfield Terminal, Dubai Mall Extensions, Etihad Arena, Mother Gate, Expo 2020, Al Sinaga Corridor, Wanjabil, MHN and Jotica projects. And presently I'm working as a lead engineer bridges and civil department in with Rambol India since last year. I also work with Choniji and partners uh, for more than 10 years in Abu Dhabi as a structural design engineer. I also work with Technip KT India and Larsen Tubro as a offshore structural engineer for close to 2 years. And I'm also a founder and contributor of online learning platforms scaleupmyskill.com and structuralbuddy.com, and I used to give a lot of blogging on structural topics in these website, so you can check out. I also have hobbies of sketching, animation, SketchUp, and blogging. Let me present the brief introduction of Rambol. Rambol is a global architectural and engineering and consulting company with more than 18,000 experts, and it creates sustainable solution for government and companies all over the world. Rambol founded in 1945 in Denmark, and presently we have 300 offices across 35 countries. Rambol deals with various kind of projects related to real estate, energy, water, transport, industrial resources, and waste, government and public and finance and investment and technology sectors. Rambol ranks 7 overall in top 100 global ranking company which focus in environmental and sustainability consulting. In India, Rambol operated in year 1997, and since then we are working here. And here we have a global work sharing with other offices of Rambol. Uh, Rambol Engineering Center, Energy Engineering Center, Digital Development Center, and support organizations, finance, HR, IT, legal, all are working from India. We have 6 offices located in Gurgaon, Noida, Mumbai, Hyderabad, Chennai, and Bangalore. And in India, we have more than 1800 experts. Here also we provide quality services to client with complete integrated multidisciplinary solutions. We are also ISO certified with 9001, 14001, and 45001. Rambul basically provide quality market and services related to building, energy, water, transport, telecom, and environmental health. Some of the iconic bridge projects that Ramboll have done is Queen's Ferry UK, which is the tallest bridge of the world, UK's tallest bridge of the world, and the world's longest 3 towers, chemistry base. And here Ramboll was the lead designer. It is completed in 2017. And the second iconic bridge that Ramboll did is Mercy Gateway UK. This is 6-lane cable stayed tall bridge. Here also Ramboll worked as a lead technical consultant, and this bridge also completed in 2017. Ramboll also delivered iconic Indian projects like Mumbai Trans Harbour Link, India, which is the longest sea bridge in India, and it is also completed in 2021. Some of iconic projects that in India that Ramboll is have done. Mumbai Trans Harbour Link Package 2, which I have already explained. Here, this particular project has a total length of 21.8 kilometer, and it has a 6-lane freeway road base, which is connecting Mumbai with Navi Mumbai. And Ramboll is working on package 2 of this project, and role here is detailed design services. And here Ramboll saved distance traveled by 19 kilometer, direction travel time by 2.5 hours. Another project is Mumbai Coastal Road Package 1. This particular project is comprising a carriageway sea bridge with a length of 3.8 kilometer, and it has two complex interchange. As you see here at the top, this is the Haji Ali area, and another interchange is Immersion Garden, which is this one. Here Ramboll involved in detailed design services. This project is will be used by 130,000 vehicles daily, so there will be a reduction of travel time of 2 hours and 40 minutes, which is significant reduction. And this will reduce the congestion, as well as also it will help in reducing the pollution. And here monopile was used to reduce the carbon footprint. Next bridge is Dubri-Fulbury Bridge. Dubri-Fulbury Bridge would be the longest bridge over water, and would span more than 19 kilometers. The bridge will provide the missing link of NH 127B, and this project is funded by Japan International Cooperation Agency. And this bridge is basically over the Brahmaputra River in India. Here Ambol is involved as a probe checker. And here also in this project, uh, around 203 kilometer of distance is saved, which reduces the travel time by several hours. Now let's move to the today's content, introduction to cable stayed. The concept of cable stayed system used by Egyptians for sailing ships, and cable stayed bridge are believed to be evolved from suspension bridge. Early Chinese people, they used the cable stayed system to construct suspension bridge out for hemp rope and iron chains. And in 16th century, a famous Croatian polymath, Fossio Virenja, drew first proposal of cable stayed bridge. We see these, the right side, this is the photograph of the first proposal of cable stayed bridge. And the bridges which we see today, they are called modern cable stayed bridge, and they are evolved once we have better construction technologies and advanced materials and in steel and concrete in terms of strength. Once they are developed, so they are believed to be developed after 1960. And after 1960 we see a lot of international projects with the chemistry bridge, and this phenomena is spread out all over the world after 1980s, where a lot of chemistry bridges were built. And as we have better strength and better construction practices, the cable stayed bridge has become first choice for engineers for a longer span. Then let's talk about the load path of the cable stayed bridge. So cable stayed bridge is an indeterminate structure. Here the deck is supported on elastic spring support from cables, and the cables are supporting the dead load through the tension on this, and where the tension is defined is T equal to W by sin theta, where W is the vertical dead load, which is a tributary dead load shared by one cable, and then theta is the inclination angle of the cable. And this way the cable transmit that tension force and convert that into and transfer the compression force to the pylon, and pylon will transfer that compression force to the foundation. And deck is also having axial compression because of this component of T cos theta, which is shown here. Here L is the span length and L1 is the back span. Now let's talk about the general characteristic. So here basically there are four type of bridges which are compared to each other based on their general characteristics. So first column shows the PSC box girder bridge, and second is for extra dose bridge, and third is cable state bridge, and fourth is cable substation bridge. And feature wise, box girder bridge have internal pre-stressing with using the tendons instead of cables, and here the applicable span length for box girder bridge is 40 meter to 100 meter, and the deck depth can be from L by 16 to L by 20 at support, and L by 30 to L by 40 at mid span, where L is the span length of the bridge. And there's no pylon required here because this is a simple girder bridge, and this kind of structure is not sensitive towards wind. And here the service stress limit for cable is 0.7 GUTS, where GUTS is guaranteed ultimate tensile strength of tendon. For next column is extra dose bridge. This extra dose bridge is named after when the pre-stressing is done through a external tendon which is coming out of top fiber of the deck. That is called extra dose. So here the pre-stressing is provided to the girder through the external stay cables like this, and this is also having a applicable span length of 80 meter to 250 meter. And here the deck depth can be from L by 30 to L by 40 at support, and L by 40 to L by 50 at mid span. Pylon height for extra dose bridge is limited to L by 8 to L by 15, and wind sensitivity is very negligible for this bridge. And service stress limit for HT cable is 0.6 GOTS. Cable straight bridge. Cable straight bridge is mainly the deck is supported by cables, and here the applicable span length for cable straight bridge is 80 meter to 600 meter, or sometimes it goes even to more than 1000 meter also, because some of the cable straight bridge they are very long even that, but this is called the economical range. And the deck depth can be a constant and can be from 2 meter to 3 meter it can have. And pylon height from the deck can be from L by 3 to L by 5, and this kind of structure is wind sensitivity, so we also need to check the wind vibration in this one. Service stress limit for cables. uh, Here the service stress limit for cable is 45% only to its GOTS values, where GOTS here is guaranteed ultimate tensile strength of stay cables. As compared to cable strip bridge, the cable suspension bridge has very longer span length. It can be economically, you can make it from 500 meter to 1400 meter, and the deck depth will be constant but can be anything between 1 meter to 2 meter. And pylon height from the deck can be L by 9. Wind sensitivity, yes. And service stress limit for cables 40% of GOTS here. Next is the structural components. Here the bridge is shown as like there are basically four components of the structural cable steel bridge. The first component which is shown here is vertical component. This is basically a tower or pylon, and this structure responsible for supporting the steel cables and transmitting the compression force to the foundation. Cables, however, is supporting the deck at a certain spacing, and it is transmitting the deck load to the tower through the tension. And the deck is supporting the carriageway or traffic. And there is a one portion which comes here, as you see here, stitch segment. This is the one once the deck is casted up to this level, and this one is also casted here. This is stitch segment or pores, concrete pour at closure pour, that we also call that is casted at the latest stage, and which is joining the deck together. And this is the main span, and this is the back span. And the next component is foundation, which is anchored to the ground and transmit the force of the pylon to the ground safely. Now we'll also talk about some structural component of towers. So tower supports cables, and here cross beam of the tower supports deck. You see that this transfers compression load to the foundation, and the shape of tower affects the torsional rigidity of cable system. So towers shape can be S shape, A shape, inverted Y shape, diamond shape, and vase shaped. There are multiple ways to make that tower, and there are a lot of iconic structure which have a different shape as well. This inverted Y shape you have seen in this Burley ceiling base. Okay, type of cables. This is the next important component. Uh, Cables are basically four types. One is parallel bar cable. Here, the steel rods or bars which are parallel to each other, and they are encapsulated in a metal duct, and there is a grout or grease in between them, and they can be added together using a coupler. And second is the locked coil strand cables. This cable is having two type of strands. The inner core has round shaped strands. They are also twisted in helical manner, and outer core is having strands with shape of either S or Z, and they are also be twisted in helical manner. This way it prevents the corrosion, and it has a higher resistance to corrosion, and also higher modulus of elasticity. Third type of cable is parallel wire cable. Here 7 mm dia wires which are arranged in a hexagonal shape like this, and this is having good strength and stiffness because there is no twisting here, so good fatigue life also here. And small wide ratio, because of this shape and round shape of this, it has a small wide ratio, so it will have a good protection against corrosion. For parallel strand cables, which are mostly used here, this is a variation of parallel strand cables, but here instead of wire, they are using 7 strands with seven they stand with 7 wires twisted like this, and yeah, and we can also define the arrangement of the cable in longitudinal directions. So this is the half type, and this is the semi half type, and this is the fan type. In half type, you see the inclination angle of the stay cable is constant, uh, and semi half time the inclination angle is varying, but the spacing of anchorage at the pylon is uniform. In fan type, the all stay cables are radiated from one point at the top. Another way of classification of cable arrangement is transverse arrangement, the single plane system and the double plane system there. So this is the photograph single plane system where all cables are in one plane, and this is the example of Udariyat Island Bridge, Abu Dhabi. And here deck has to be adequate torsional stiffness to resist the torsion force, because cable will not help anything. In double plane system, steel cables are provided in a two planes, as we see here. This is a Patla Bridge Noida, and here the tower should have either two plane vertical system or two plane incline systems. Anchorage located either outside of the deck structure or inside of main girder. This is the example of stay cable anchorage details. So this is a stay cables, and this is the deck. This is a typical example. Stay cable have a lot of component. So we see here, this is the anchor cap, a wedge plate, and the ring nut. Ring nut is a kind of base plate which is bearing at the face of this back side of the deck or stressing beam, and this portion is called anchorage zone. From here to the top point where this stay cable is protecting outside, that point is called transition zone. Here we also need to have the guide deviator and bearings. So this is the details. These are the deviators which are provided to make the strands little separate from each other, so that it will be more effective when it is stretched. And from here to here, it is called the free length. And again, in pylon, the arrangement in pylon, if it is concrete, is something like this one. As you see, these are the concrete pylon, and the arrangement of stick cable is like this one. For steel pylon, arrangement can be like this one, with a big gusset plate connected to the here and connected to the pylon, or like this one, or this one. Some stay cable, they also need a shadow, so it all depends on the requirement. And this is another arrangement of the stick cables. This is a deck with having a single plane system. So a stick cable is anchored at the middle of the deck, and this is the anchorage details. And this is another arrangement where the stick cable is anchored at the end edges of the deck, and here we see a kind of anchor block. And for steel steel deck superstructures, the steel cable arrangement of anchorage can be like this one, and these are some photographs for steel deck, and this is the steel cable anchorage for the concrete deck. Now, steel cable protection against rain and wind and vibration. So steel cables are sensitive towards vibrations. So to check whether it will be okay, uh, we check the scrutons number of the cable, which is defined like this. Scruton numbers is linearly proportional to the damping ratio of each mode, and is linear density of cable, and also inversely and also have a 1 by d square for the diameter of cable, and density with this formula. So based on this, if the scruton numbers are greater than 10 uh, for cables, then no further mitigation required, the cable will be fine. If scruton numbers are greater than 5 but lesser than 10, then that can also be okay, along with we need to have some effective surface treatment. And what measures we can make to reduce the vibration? The first measure is surface treatment. So stay cable either have a as you see here, axially aligned protrusions, or helical fillets or rifts, or lumped surface roughness. These kind of arrangement reduces the vibration of the stick cable. And second is cross ties. If you are providing the cross ties like this, then the effective length of the stick cable is reduced, and this will reduce the screw turns. This will increase the screw turns number. And external dampers is the third measures. So external dampers, which is friction or viscous type, they they can be applied at the location near to the anchorage of the stick cable with the deck, like this one. A few things which we need to check: if a pylon is made of concrete, and those check are lightning check, so protection against lightning. So why this is needed? Because if there is a lightning strike, uh, then then if the mass of the concrete is not earthed properly, then there will be a huge falling of the concrete. So what we do is, we connect the reinforcement mass of the pylon through a measures where it should get earthing directly. And for that we need basically a collector lines which is made of copper. Here this collector line is connected to the anchorage point of the stick cable, and then it is connecting to the transition line, and transition line is also connected to the mass of the reinforcement of pylon, and this way it goes to the down in the foundation. There are certain things which we need to remember, that the collector line should have 50 mm square minimum area, and it should be made of copper or any ductile material with good conductivity. And the second is this transition line, which should have minimum 200 mm square. For transition line we can use the welded bars, group of bars. Next component is deck. Here deck has different shapes, and it depends on the flexure, torsion, rigidity, and carriageway width, wind induced vibration, and deck depth, 2 meter to 3 meter max. So you see here, these are the various type of deck based on the requirement, and it can be done. One thing we need to make sure that deck also need to be checked for wind vibration. So if the width of the deck is greater than 10 times depth of the deck, and span length by 30, then that particular thing, even if it is a open section like this one, it should be okay, and there should not be any wind vibration issue. But if it is not so, then we also need to provide a wind nose here. And also, if this width is lesser than L by 30, then we need to have A-shaped tower with additional required for torsion rigidity. Next component is foundation type. Foundation, there are basically four types, we can say: piled foundation, caisson or well foundation, strut footing, and mat foundation. So we know that pile foundation is applicable where the soil near the surface is very weak or compressible. Here piles can be driven into deeper, stronger soil or rock layer, and it can be end bearing or friction piles. For caissons or well foundation, we need to have a large diameter vertical shaft drilled into the ground and then filled with the concrete. And here used in areas where piles are not suitable, such as if it is inside the sea or river bed, then we normally use caisson or well foundation there. For spread footing, also known as flat foundations, used when soil near the surface enough to support the loads, and it spread the load to large area to reduce the pressure on the soil. And the next is mat foundation. Here it consists of large concrete slab that support multiple pier or columns and used when the soil conditions are weak. And this helps to reduce more evenly stresses across a large area. So some of the advantages of cable steel bridge. So cable steel bridge is a highly structurally efficient and having a good strength to material ratio and better load distribution and material efficiency. Second is the aesthetic appeal. It looks very elegant and modern structures. Third is the economic consideration. It is very cost effective, less time for construction as compared to suspension bridge. And fourth is versatility and adaptability. Here a lot of things can be changed and can be used based on the span length, medium to longer bridge, versatile for different crossing over river, valleys and highways. And in terms of maintenance durability, it has good maintenance. It has reduced maintenance as compared to suspension base and can withstand hard environmental condition. And in terms of engineering and design flexibility, yes, it has have a lot of flexibility in designing various component of the chemistry base as compared to other bridges. Can have a single pylon, multi-pylon, fan arrangements, harp arrangement of the cables, lot of things we can play. Other is it can handle traffic and load very much, very good, because it can handle the vehicular load or railroad or pedestrian load. This now let me present a case study where a MIDAS software was used. So this is a iconic bridge. Here this bridge is total length of 130 meter, and here this is a upcoming bridge in Mumbai. Here the pylon shape is in the shape of zero, and this is a kind of very iconic structure. And here the total cables used here is 20 number of cables with 6 pairs in the main span and 4 pairs in the back span. And this is another view of that bridge. So this main span is shown here and this is back span, and there is a water channel here and there is existing road here. The spacing of the cable at the deck level is 9.1 meter and the spacing of the back span is 7.5 meter, and the deck depth is 3 meter. And here cable stressing end is can be done either from the deck side or can be done from the pylon side as well. And this is the concrete segments. The deck is a precast segment deck. So the main span is having almost 24 segments, and here basically all these segments are having a uniform length of 3 meter. But in the back span, some portion of that area is a cast in situ on false work, and some portion is having a precast segments with varying length from 2.2 meter to 3 meter. You see here some segments are stay segments with the stay beams shown here. And the stay segment looks like this, and the normal deck segment where no stay cable is there is something like this, which is singular box girder base. And there are some blisters shown here as well. And cast in situ portion is normally 10% of the main span. So total span. So here it is some portion of this which is a part of the main span, and some portion of this which is back span, that is cast on false work. This is the longitudinal global model which is developed in the MIDAS civil, and here the deck element and all these elements are modeled as a line element, and the cables are modeled as a cable or tension only cable elements. I'll explain the modeling part in the next slides. This is the overall another view of that model. And here you see this is 80 meter, and we also here this is the west approach and this is the east approach that are done by others, but this was also modeled here just to take the global seismic effect of this one. And here the stay cable angle varies from 18 degree to 31 degree in the main span, and from 24 degree to 34 degree in the back span. And this portion which is shown here, this is the distance where the stay cables are starting. Now let's discuss the modeling strategy. So in this modeling strategy, the model is done using a linear element, line beam element of MIDAS 7. And here you see this is the midline, which is representing the deck's center line, and it has uh, the section property is similar to the design, and it's given uh, like this. And the stay cables, they are modeled as a cable only element here, and that stay cable are connected to the deck using rigid links as shown here. And this line beam element for bridge deck is here, and these two lines which are shown in both the direction of the girder, these two lines, these are the dummy element which represent the railway track. It's because this bridge is supporting two track of metro. And this is the west approach of the bridge, which is grillage beam elements for steel concrete composite deck. And for these are the piles. Piles are modeled as a line element with the lateral spring supports from the soil. And at the bottom of that, the vertical spring support representing the end bearing of pile is provided. And this pier is named as P476, P477, and this is the pylon which is named as P478, P479, and P480. The east approach is modeled as a U-trough precast concrete beam element, and a pile group stability is provided here and here. And this model with the east and west approach is all is done because to capture the seismic effect of the global things. Okay, one more thing here which is important, that these are the detail 1, 2, and 3 of the bearings of that so this is the pylon area. In the pylon area there are basically two bearings used. One is fixed bearing, another is transversely guided bearing. These are spherical bearing are being used here. And for the west approach, the portion of the west approach span deck, they are supported on four bearing. Out of four, there is a one longitudinal guided bearing and three pod bearing. And cable straight portion of the deck is supported on two bearing, longitudinal guided bearing and the free bearing. And both are sharing one pier head, is shown here, and the connection for that is using through a elastic rigid links. And for each approach, again the bearing here is one is free bearing, another is longitudinal guided bearing. And the east approach span is supported on top of the main back span of the cable strip base with elastomeric bearing. Here concrete properties, common pier pile caps and piles of the model are having 40 ampere of cubic strength, and deck is having 60 ampere of cubic strength. Uh, Time dependent effect are used based on CB FIB model code 2020, and pre-stressing uh, of deck is used 15.2 mm strand with nominal strand area of 140. And reinforcement grade was considered 500D in the design. Structural steel is used 350 ampere for the pylon, And for stay cable, the nominal diameter of strand was used 15.7 with nominal strand area of 150 mm square. Now let's talk about the basic loading on the bridge. So in the MIDAS, there is a very good feature of self-weight and other loading applications. So the self-weight is calculated based on material data what we are providing in the software, and the material data also have the density and also and we also signify what direction of the load is to be considered. So in the z direction we are giving -1, and then using the gravitational acceleration the software automatically calculate the model weight. For pylon, which is made of steel instead of concrete, this is made of steel and there are a lot of joints inside in that, so the weight of this one increased by 10%, and that is modified in the weight density of this one. And for longitudinal global model, uh, this is the sidereal loading, which comprises the diaphragm loads, cable stretching beams, PT blisters, steel parapet, handles, rail pads and planes, and some miscellaneous wearing courses load, and cable troughs, cable trough load. These are applied as a UTL and some of them are applied as a point load, and these are as per the design basics. Then creep and shrinkage effect in minus civil, that is used through a creep coefficient curve, which is shown here, and this is based on CB FIB code, and this is the time dependent material function which is shown here, uh, and this is also a another time dependent function of different material. Okay, and this is the tendon properties which are used in pre-stressing. So 19 strand tendons and 12 strand tendons are used. Uh, this is the top tendon arrangement of the deck, and this is the bottom tendon arrangement of the deck. These are for cantilever tendons and these are for continuity tendons. Now, we also consider a detailed construction stage analysis of the base. So, while doing the construction stage analysis, there are some options in MIDAS 7 which we need to uh, activate, which is shown here. And based on activation of this, as I earlier mentioned, that stay cable was modeled as a tension only cable elements. So tension only cable elements is becomes non-linear because it is having a catenary effect. Sagging of the cable reduces the stiffness, and the stiffness depends on that sag as well as its elastic properties. So that stiffness software calculate using this concept, which is K combination is 1 by K sag plus 1 by K elastic. So based on that, the MIDAS calculate the equivalent truss element stiffness of those cables. But that we need to, once we activate this here, then it will consider in the post construction stage. This slide presents the basic construction stages that are considered in longitudinal global model. So there are total of 32 construction stages considered in this model. The first construction stage is when the foundation pier and center pylon are constructed, and then the second stage is when the back span segments are erected on falsework and stressed, and then cast sensitive segments of near to the pylon, they are also casted in this stage. And the next stage, the first three cantilever segments of main span are erected using segment lifter and stressing of the top tendon done, and then installation of first pair of main span cables are erected. Same way, the next stage, the erection of fourth segment of main span are erected, and top tendon are stressed, and the installation of first pair of backspan cables are erected. Same way, the next stage, the fifth segment of main span was erected and its top tendon are stressed, and then installation of second pair of back span are erected to balance out the loads. So this way, next stage is erection of sixth segment of main span and top tendon stressed. Then erection of second pair of main span cables are erected. So this goes like this. This way, all main segments are erected one by one, and it's their top tendon are stressed. And once two to three segments are erected in one go, then the corresponding main span cable are erected. And to balance out that, the back span cables are also erected. So the construction stage goes like here, then it goes like here, then it goes like there, and it reaches up to the end of this one where all the main span and the back span stay cables are erected like this. Once the 20th and 21st segments of main span are erected and the stressing of their top tendon are done, then last three segments of the main spans are erected on false work, and then a deck closure segments are casted, and then the continuity tendon of main span are stressed. And once this stage is completed, then the west approach and east approach deck is installed, and then the ideal and long-term effects are applied on the model. Now for cable tuning and cable pretension, that was a very important task in cable state bits. So this is having lot of iteration, because initially the stay cable tension are determined considering the same global model with only dead load and pre-stressing, and then we have used the UDL unit tension on those pre-stressed cable. Initial model was developed, and then using the unload load factor and cable tuning option MIDAS civil, which optimize this thing after adding the constraint on the deck and the pylon. And the constraints will be like, we give the software a range of moments, that the moment at sagging and hogging location should be in within this range, and the deflection is also limited to a this much value. Then software will optimize that, and then it gives a pretension values, and then we apply that pretension value on the model and rerun it, and we check whether the deflection we and moment that we want is within that limit. So this kind of iteration are done in MIDAS civil, and then we got the initial cable pretension. Now once we get the initial cable pretension, we do the backward analysis. So we, in the backward analysis, we deactivate the cable from the final stage. We deactivate the cable and deactivate the segments one by one, and we reach to the initial stage. And this way we evaluated the pretension at end of each steps, and then those pretension are further used in forward analysis, and there we also add the effect of creep and shrinkage, and this way these iterations are done 3-4 times to tune the cable stresses so that it satisfy all our requirements. So based on that, this cable tension force are evaluated, which is shown here, and then this we apply the live load, and here the live load is like two configuration of live load. All Axle load are 17 tons, and there are maximum 6 cars considered in one train. And the curve is and the bridge is curved, so it also has a radius of curvature 352. You see, and this is the live load, centrifugal force applied as a zodiac, and the braking and traction forces are also applied as shown here. And here the dynamic allowance for live load is considered 1.3 for longitudinal analysis and 2.0 for the transverse analysis. Wind load are basically applied in the model. Wind load condition is, there are two cases considered in this one based on IRS code. One is unloaded bridge condition and another is loaded bridge condition. The bridge bridge condition, the wind speed is 117.5 km per hour, and for unloaded bridge condition 158 km per hour is considered. A wind application are considered, and various angle of the wind is considered in while applying that load, and that will be acted as a separate cases. And the angle varies from 0 degree to 90 degree with 10 degree of interval. Temperature load are also applied in the bridge as per the design basis, and here all kind of temperature load including the differential temperature between the stay cable and the deck and stay cable and the pylon are also considered like this. Maximum temperature range for pylon is 42.4 degrees Celsius and minimum temperature minus 37.4 degree. Temperature gradient are applied in MIDAS based on its the deck geometry and the thickness of the concrete material, and the painting is been applied the gradient and then it is applied like this. Bearing friction force, 10% of permanent reaction in expansion and contraction applied as a point load, and a case of cable loss, which is extreme case, is also checked based on PTI DC45 guidelines. Here first the stay cable are evaluated, the pretension is evaluated for this ULS case, and then uh, that particular stay cable is deactivated and a point load is applied at the anchorage location of deck and the pylon with a additional dynamic factor of 2.0, and then the rest of the stay cables forces and the deck forces moment are extracted for this particular load case, and compared with the other ULS cases and checked which one is governing. The seismic loading using elastospectrum response spectrum method is used here. Acceleration, horizontal acceleration coefficient is evaluated based on response modification factor of 1, importance factor of 1.5, and seismic zone 3, and soil condition of medium soil side. And this acceleration coefficient is directly feed it to the MIDAS civil. And for various component checking, the response modification as per IRS code is different. Like superstructure it is 2, RCP is 3, for steel pylon it is 1, and other also it is 1. So that we adjusted using the load combinations factor. Differential settlement of foundation is also considered in the global model. So for this space, a long-term differential settlement of 12 mm is considered as shown here. Design load combination as per IRS CBC that is being used here with additional seismic load case as per IRS seismic code 2020. And cable loss case and cable replacement are checked using guidelines of PTI DC45 with these load combinations. And this way the MIDAS Civil has we have developed the design load combinations in MIDAS Civil, and which are used for the extra. And then the longitudinal model is checked for stresses limit as per the IRS codes. So for pre-stress concrete material, the tensile stress for segmental deck is considered 0 for service condition for SLS1 case. For compressive stress limit in concrete is 0.4 FCK, and 0.7 FPU is the limit at transfer for tendons. And tendon maximum jacking force considered is 0.8 FPU. That is the maximum limit, but we consider 0.75 FPU. And erection stress limit during the construction stage, the compressive stress limit is 0.4 FCK and tensile stress limit is 1 FPA. For steel cable stress limit, we followed FIB Bulletin 30, which is 0.45% of GOTS is considered for SLS and 67% is considered for ULS. And for construction stage and cable replacement, 60% is considered. This is the typical stress deck stress diagram, and for SLS1 case. This is for SLS envelope case, the maximum compressive stress, which is within that limit. And these are the cable stresses at SLS envelope case, and that is also within that 0.45 FPU. This is a typical longitudinal bending moment diagram of the deck in MIDAS Civil. You see here, this is the main the deck portion, and this is the pylon portion. Now let's discuss the transverse model methodology. So for this bridge, the transverse model is having two model developed, one for main span and one for back span. And here the deck is the model as a plate element, and wherever there is a stressing beams, those are modeled as solid elements, and diaphragm are also modeled as solid element. And here, instead of modeling the stake cables, uh, the the spring supports at the Anchorage location is provided, and the stiffness of the spring support is determined through a unit load method in the global model. And only the vertical spring stiffness is applied here, and the lateral effect of the stake cable are applied as a unit load, as a point load, based on the component of the stake cable forces from the global model, and those components are applied in SLS combination and ULS combination separately. And these are other SIDL loading in this transverse model as well, shown here. And this is the steel parapet load and steel cable forces we see here. Live load positioning, various live load, critical live load positioning is considered. Eccentric load case, maximum live load case, and based on that, uh, the forces are extracted. These live load cases are enveloped to each other and is being used in the load combinations. Then the derailment load case is also considered, which is using IRS based rules appendix XX3. And this derailment load case are considered for ultimate conditions and stability conditions. The extreme cable case is also considered similar to what we consider in the longitudinal, but here the dynamic factor was used as a 2.0. These are the sample design force contour for transverse design of deck. So this portion as we see here, this is ULS transverse moment at haunch location of the deck slab, and this is the transverse moment at web location of the deck. And these are the shear force contour for haunch location, and this is the shear force contour at the web location. Now similarly, all the elements of the deck are extracted from the analysis results and being used for the design. For the checking of design of stressing beam, the transverse model is used with the only replacing the solid model of stressing beam to the line model here. Rest of the deck is modeled as a plate element, and here the stressing beam is a line model which is connected to the neighboring plate element of the deck using elastic rigid link as shown here, and also the anchorage point where the stay cable is going to be anchored, that particular node is connecting to the stressing beam using a rigid link. These are the sample design forces of a stressing beam for ULS, ELS, and SLS load cases. So all these forces are used in the design of stressing beam as shown here. Now there is another analysis which we use for local anchorage check, and that require 3D modeling. So there is a very good software of MIDAS, which is MIDAS FEA Annex, which is highly recommended and is being used here. And in this one, if only portion of bridge is modeled, uh, that geometry is there's an option in the MIDAS FENX where we can export the geometry from a AutoCAD file. So that was being exported and it's been meshed, and then there's a other side of the bridge, like one side we have restrained it, and here only the jacking force is applied as a stressing beam, as a stress at the area where the tendon bearing plate is there, and then stresses are stress contour are extracted from the model after running the analysis, and this way we got the stress distribution in 3D. So from this stress distribution we determine how much is the tension in vertical direction and how much is the tension in the horizontal direction of different phase of this, and this way a equilibrium reinforcement is evaluated. So if you see here, this is the anchorage phase of the area, and here the stresses in x direction, which is this one, is shown. This red portion is the tension here, and there is a one section cut here, A is shown here, and we see the stresses at the back face of the anchorage as well, and this way we know, okay, these are the horizontal rebar we need at these locations. Now these stresses, once we got these stresses, then we select the region, that how much is the region with this much average stress, and based on that we converted that stress into the tension force, and this way the additional anchorage additional reinforcement due to this equilibrium are determined. Same principle also applicable for blister segments, and here also we model like this, and then we applied the stressing force from the PT, okay, and and we once we analyze this, we got the stresses, and these stresses are further used for reinforcement, additional reinforcement due to anchors, and same concept is used for stay segment as well. So this way we combine the transverse flexure reinforcement from the transverse analysis, and we combine the shear and torsion reinforcement from the longitudinal analysis, and additional equilibrium reinforcement from FENX analysis for each segments, and then we combine the total reinforcement requirement, and then we determine how much is the idealized reinforcement based on the selected rebar and the uniform spacing, and this way we provide the reinforcement. So this is a typical deck and the reinforcement arrangement, and at location of the tendons, since if the tendons are like provided at the uh, flanges or at the bottom flanges and the top flanges of the box girder, and if the spacing is lesser than 300, then we need the also additional hairpin bars in both the direction of the in both side of the east tendon, and with a spacing let's say 400 or 450, and this is to prevent any wobbling of the tendon, because and rest of the you see here, this is reinforcement which is provided here is a transverse reinforcement and from transverse flexure and the equilibrium RC due to either anchorages or blisters. And for middle portion also the transverse flexure and torsion RC and equilibrium RC. So we know that for torsion the outer links which is closing this, that is utilized in the torsion, so that is also added here. And same cheese for web, the transverse flexure plus shear plus torsion and plus equilibrium RC, and same thing is for bottom, transverse flexure, torsion and equilibrium RC. So this way for each segment the reinforcement is determined. This slide presents the design challenges and some recommendations. So for this project, there was a one design challenge, which is a cable pretension. So cable pretension determination is a process which require a lot of iterations, and also it requires to do a backward analysis of construction stage and forward construction stage analysis of the base. And here, MIDAS unknown load factor and cable tuning method is very useful, and this help to solve the cable pretension in less time. The next challenge is stay cable anchorage reinforcement detail. For some stay cables which has a lower inclination angle, uh, their detailing or reinforcement is quite complex, because here we need to avoid the classes of stay cable local anchorages forces with the reinforcement of stressing beam in longitudinal directions. So here the 3D detail model in AutoCAD is very helpful. And next challenge is uplift of deck of backspan at pier P479. Here the deck is getting the uplift force at service condition as well. So for to solve that one, we propose a tension rod ties of the deck to the pier head as the alternative to the uplift bearing. And next challenge is the stay cable setting out points determination at deck and pylon. So that was also a very challenging task, and here we have used extensively we have used 3D AutoCAD model for determining the exact stay cable setting out points in global coordinate system. And next challenge is for covering all the design of elements, we need multiple code references, because uh, one code of IRS or IRC does not cover all the design elements. So we also need to do the fatigue, seismic, cable loss, replacement cases, wind vibrations. So multiple citation of codes and references are needed. Based on these challenges, I can recommend few recommendations like there should be a beam modeling for these kind of complex beams that can be very useful to detect classes of tendon or reinforcement, and also to visualize them before actual construction to avoid any issues during construction. Next recommendation is like MIDAS has very good package of software which is MIDAS Civil, extensively used for longitudinal modeling and also used in transverse modeling. And MIDAS FEA Annex is also useful for 3D solid modeling using Anchorage analysis. So they are a very good tool for predicting the behavior of the bridge elements and under these loads. And next is a comprehensive design code which is required to cover design of all elements of cable sheet bridge in one document. So conclude my presentation. Thank you very much. If you have any question, please ask. Also, you can contact me for any inquiries or any future projects which you want to discuss. This is my email ID, s2@rambol.com. I will be happy to answer your question. Thank you very much.